email during the week asking for some help with one of the problems, and I responded. This person was having problems with the cosecant and the secant problems. Not that we did them last week, but they're really not a whole lot different. So let me start out with problem number 28. 5 times the cosecant of theta minus 3 equals 2. Probably the first thing I would do is I would try and get the cosecant term by itself. So I would add 3 to both sides, so 5 cosecant of theta equals 5. And let's see, divide both sides by cosecant, divide both sides by 5, so cosecant of theta equals 1. All right, I'm getting a little nervous here. I hit the record button, didn't I? Okay, good. So I don't want to go through this and try and hit the save button and there's nothing there. All right, that's good. Now cosecant, we're just not as familiar with cosecant as we are with other things. So let's think of cosecant in terms of its basic functions. Cosecant is what over what? 1 over the sine. So this is really 1 over the sine of theta equals 1. And if I multiply both sides by the sine of theta, then on the left-hand side I get some nice cancellation. Sine of theta disappears, and I'm left with the equation 1 equals a sine of theta. So that's not bad. All right, that gives us something that we can kind of dig our teeth into a little bit. Let me rewrite that up here. Sine of theta equals 1. But I need to know what theta is. What can theta equal? So, okay. To get theta by itself, you're going to use the inverse sign. Because the inverse sine and then the sine, they're opposite functions of each other, inverse functions of each other, and they're going to cancel each other out. So sine inverse of sine of theta is just theta. And over here, we're left with the sine inverse of 1. Now let's understand what this means. You're asking what angle has a sine equal to 1. Now sine is your y coordinate, so where's the y coordinate equal to 1? Pi over 2. Ooh, I like that. You gave it to me in radians and not degrees. Pi over 2. Great. It actually goes a little bit beyond that, right, too, because sine is periodic with period equal to 2 pi. So every 2 pi, it repeats itself. So I can put 2 pi times n, where n is an integer. Now technically in this problem I don't need to do that because they're just looking for solutions in the interval 0 less than or equal to theta less than 2 pi for problem 28. And you're only going to have one solution in that interval. But this is the more general solution for those.
N is the same as k, right?
N, k, yeah. This is just an integer. Now, maybe I'll play with this one as a nice example. But let me pause here for a second. Are we okay with what I did with problem number 28 here? All right, good. Now, at some point, you're going to need to clean these things up a little bit and list out several solutions. So to make this a little bit easier, I'm going to do two things. First of all, I'm going to get a common denominator between these two. Right now, this denominator is 1. So a common denominator then would, of course, be 2. If I multiply by 2 over 2, let's see what I get. I get pi over 2 plus 4 pi n over 2. I'm going to do one last thing here. I'm going to factor out the pi. All of this is over a denominator of 2. If I factor out the pi from this first term, what's left behind? 1. plus 4n times pi. And this, I hope, would make it really easy for you to plug in values of n to figure out, all right, well, where do these things work? Where do they meet? You know, what are the solutions? So we can make a little table here, values of n and the corresponding values of theta. And what this is going to show is you're just going to get a nice regular set of multiples of pi over 2, specific odd multiples. So if n is 0, then theta is, well, that's just a 0, so that'd be pi over 2. If n is 1, then what would the coefficient here be? Yeah, 5 pi over 2. Thanks, Charlie. And then 2 would be 9 pi over 2. 3 would be 13 pi over 2. I mean, you can get as many as you want from there. But once you've cleaned it up, it's not so bad. Let's see that that's actually true. And let's see that in a visual way. Now, I'm not going to graph all of it, but let's take a quick look at a graph of just the sine function. Y equals sine of x, and then y equals 1. Now, what I want to see is where these things intersect. And the cool thing about Desmos is that it'll help you find these exactly. So there you go. There's pi over 2, 5 pi over 2, 9 pi over 2, etc. And you can find as many as you want. But they all follow that same pattern. They're kind of a peculiar odd multiple of pi over 2. So, nice. You can do that on your graphing calculator too, if you wanted to. You can set it up. The only problem in your graphing calculator is you're going to get a decimal value here. You're not going to get something nice and even like 13 pi over 2. All right, how are we looking on that one? Good. By the way, before I forget, let me do this. R equals, let's see, 5 times, let's see, 1, let's see, 1 minus sine of x. No, sine of theta, sorry. Where's theta? Theta. There we go. So before I forget, happy Valentine's Day. Yay. And you thought math had no romance in it. All right. We'll see this a little bit later on. It's called a cardioid. Okay, so let's get back and do a couple more of the trigonometric equations from section 3.3. No, not for this particular problem, but yeah, just the pi over 2 in this case. But I do want you comfortable with what we did here, because there are some problems where you do need to go a little bit beyond that. Okay? So, great question. Let's try, let's do a couple with the tangent. I didn't get to work with the tangent / cotangent the other day, so let's work with that. So problem number 20. Tangent of 2 theta equals -1. Okay, well, one thing I want you to remember about the tangent is its period. Period of the tangent. What's the period of the tangent? Pi. Well done. Sine and cosine have a period of 2 pi. The period of tangent is pi, so it repeats itself a lot more often than the sine or cosine graphs. Okay. So, just like the last one, we want to get theta by itself. So I've got the tangent of 2 theta equals -1. how am I going to get this theta, or at least start to get this theta by itself? What function can I apply to both sides to start undoing things and getting that theta by itself? Inverse, good. So that'd be tangent inverse and the tangent inverse of -1. Now, I don't expect you to have all these angles and things like that memorized. And if you don't, that's fine. Nothing wrong with that. What I would suggest is that you use your calculator in degree mode to figure out some of these things. All right? Because if you have it in radian mode, you just might not recognize it. And that's fine. Nothing wrong with that. But it's probably easier to recognize this in degree mode. So another one in degrees. All right, let's change this over to radians. Inverse tangent of -1, and it gives me -45. Oh, that's in radians. So if you recognize that as being -pi/4, good on you. But if you don't, then put your calculator in degrees and try it there. Now you get something that's a little bit more recognizable. So -45 degrees is really -pi/4. And that's equal to 2 theta. Okay. Now at the start of this, I reminded you.
There is like 2 theta. Is there like a trig identity for 2 tan 2 theta that we can use, or there's?
You can, but you'd make your life a lot more complicated at this point.
But we did some problem that it was homework and we used a trig identity and it worked.
I'm sure that I know there's a trig identity for tan 2 theta, and we're going to do that later. But I think you'd be making your life a lot more complicated if you applied. On this particular problem, you would, yeah, it'd be like squirrel hunting with a bazooka.
But on other problems, we can use it if it works.
You can always use the trig identity, but I think this one would be the long way to pursue this problem, because you're almost done. All right. Now the thing that I was going to mention here is that tangent is periodic with period of pi. So I'm going to put pi times n, or n times pi, or n times k. N or pi or n or k, whatever you use, is an integer. So as I said, we're almost done here, right? I don't know. What do you think? Should we make Ahmad do this one? Yeah. Ahmad, what do we have to do to solve here? Divide by 2. Some of you might find it easier multiplying by 1/2, because if you try and divide this by 2, you look at that and go, I don't know. So if you want to divide by 2, if you can do that, that's fine. Multiply by 1/2, that also works. So the 1/2 and the 2 cancel each other out. Theta is -pi/8 plus pi n over 2. Cool. Let's play the same game with this one that I did with the last one. Let's clean this up a little bit so that I can figure out what it looks like in general. Greg? Yes. Yeah. Because if you did it afterwards, then you'd have pi n, and you should really have something about half of that. All right, so good question. Yeah. Definitely when you account for the fact that this is periodic, you want to put in that periodicity now before you finish solving. Okay? Right. Right. So like on the last one, well, on the last one I didn't have to divide here, but if I did have something that I'd want to put in that 2n pi before I divide it. So yeah, good question. Thank you. What's the common denominator between these things? 8. So I need to multiply this by 4 over 4. And that gives me 4 pi n over 8. And if I clean this up by factoring out the pi, I get -1 plus 4n times pi over 8. And again, you've got a nice friendly expression with which to work. So if I plug in values of n, I can get values of theta, 0 would be -1, would be negative pi over 8. 1 would be 3 pi over 8. 2 would be 7 pi over 8, etc. I can get as many as I want from here. In fact, if you're feeling extremely lazy, here's what you can do. You can type in that function, -1 plus, I'll use an x, -1 plus 4x, and do a table. Hit the second key, then the table. Let's change the setting on this. Oh, it's ask. Good. And then just ask your calculator to figure out, all right, well, what if I put in a 0? What if I put in a 1, 2, 3, 4, 5, etc. So you can get all the values that you need here. Let's take another look at this graphically, kind of like we did the last one. So I'm going to graph two functions. Y equals tangent of 2x, and then y equals -1. Let's zoom in a little bit just to make it a little easier to see. But when you look for those points of intersection, you're going to see points that we were seeing. This one's your -pi over 8, 3 pi over 8, 7 pi over 8, 11 pi over 8, etc. So works out pretty nice. How are we doing on problem 20? Okay there? All right. Let's try problem number 26. Square root of 3 times the cotangent of theta. Oops, let's change the view here. Square root of 3 times the cotangent of theta plus 1 equals 0. How would we start this one? How would you start it? Yeah, I'd move the 1 over. Square root of 3 cotangent of theta equals -1. Cotangent of theta equals -1 over root 3. And, you know, if you're like me, I'm just not as well versed with that cotangent as I am, say, the tangent. So let's remind ourselves that the reciprocal of the tangent is the cotangent. Okay. Well, you know, I don't think I've recommended this to a class before, but I will here. It'd be nice just to take the reciprocal on both sides. Got to be a little bit careful doing this, and I really only recommend it if you have two fractions and you're just taking a nice simple reciprocal. If I take the reciprocal on both sides, what equation do I get? Tangent of theta equals -square root of 3. Oh, okay. That's looking a little bit better. Now what do? Yeah, inverse tangent, right? I need to get theta by itself. So the tangent inverse of the tangent of theta is the tangent inverse of -square root of 3. Now, being the very helpful guy that I am, I'll simplify the left-hand side for you. If it's theta, why don't you figure out what we get on the right-hand side? personally, I'd take out my calculator and do it on my calculator in degree mode, unless you're really good at recognizing angles and radians. You should get a negative angle. That's okay. We'll work with it. Yeah, negative 60 degrees. But of course, if we were to do that in radians, what would it be in radians? Yeah, negative pi over 3. Alright, so negative pi over 3. What else should I add here? Period is pi, so you're close. I know where you're headed. It's n pi, but then you need a common denominator. So to get that common denominator, I'll multiply both sides, or numerator and denominators, by 3. So it ends up being 3n pi over 3 for theta. Or better yet, factor out the pi, negative 1 plus 3n pi over 3. And now it's nice and neat. You can get as many solutions as you want. Just plug in different values of n. Is it worth graphing this one, or are we okay without the graph? Yeah, question? Both sides. So the reciprocal, let's flip both sides. I did. Well, I took the reciprocal of both sides. It's not the same thing, though. The reciprocal of 1 over square root of 3 is square root of 3. All right. I did it to both sides, though. No, I'm not. No. It's all right. That's why they pay me the big bucks. So, so when you have the reciprocal of something, a over b, those things switch sides, right? So you're going to have b over a. So on the left-hand side, there's my numerator, and this is my denominator. So when I switch those, I mean, technically there's a 1 in the denominator, but I didn't show it. I didn't really write that. And technically here, now I didn't do anything with the negative sign, but technically here there's a 1 in the denominator. So, kind of like the previous one, when I took the reciprocal, that became the denominator, that becomes the numerator. So I did switch actually both terms. Okay. Why don't you talk to me during the break, and we'll look at it some more, okay? All right. Last but not least, I mean, you can finish this up and list out as many solutions that you want. Typically speaking, a lot of these problems just ask you for solutions in the range of 0 to 2 pi. So n equals 0 doesn't work, but n equal 1 would give me 2/3 pi. N equal 2 would be what, 5/3 pi. N equal 3 is going to go beyond 2 pi, so we'll just stop there. All right. Okay. One last one for this section, and it's going to get kind of long. fact, you know what? I'm going to approach this one a little different than maybe I had written in my notes. We're eventually going to work on problem 66. But I want to kind of do a couple pre-problems that build off of the stuff that we've been doing. So, for instance, if I was to ask you for the general solutions of cosine of theta equal 1, what would those be? Or the solutions of cosine of theta equals 1/2. Where is that true? Well, let's think about things, a couple of these things. I'll work on the cosine of theta equals 1/2 with you. And then I want you to think about cosine of theta equals 1 on your own. Okay. Cosine is which coordinate on the unit circle? X coordinate. All right, so I've got an x coordinate of 1/2. That's what I'm being told. X coordinate is 1/2. That's going to happen at 2 places on the circle. Unfortunately, when you do the inverse cosine, it's only going to give you one of those 2 solutions, isn't it? So you're looking at this and go, okay, I got that. Theta equals a cosine inverse of 1/2. My calculator spits out 60 degrees. I know 60 degrees is pi over 3. Okay, that's great. That's this one. But there's another one. And we want to list that using a positive angle. So I want to know, well, what's that angle here? One in blue. What else could they equal? Well done. All right, so a couple ways to think of it. If we know this is a 60-degree angle, then this is a 60-degree angle this way. But that's a negative angle. To get it this way, you can think of it as 360 all the way around minus 60. So the other possibility here is a 300-degree angle. And I think I heard at least one voice say that that was 5 pi over 3. Now both of these get the plus 2n pi that we're familiar with. Plus 2n pi. And I'm sorry I'm not consistent. Sometimes I write 2 pi n, sometimes I write 2n pi. But those are your 2 solutions in general. Now, why don't you see if you can't think about this one and write down the solutions to that one in general. check the sound. Yep, got sound. Okay, cool. All right, so cosine of theta equals 0, or I mean cosine of theta equals 1 when you're right here. Now there's two names for that, 0 or 2 pi. Actually, there's quite a few names for that if you go beyond this. But let's just keep it simple. Choose a 0. So theta equals 0. Now, if you want to encompass the fact that, gee, if I go around again, or again and again, 2 pi times n, theta is just a multiple of 2 pi. That's it. So those are your general solutions there. So we're okay with that one? This part of 66? All right. There's still more work to do. We actually haven't done the work to get to this yet. But that's just the happy ending. Let's see how we get there. And I'll give you kind of a quick reminder of something that we're going to use in the next section. And that is our even-odd identities. Sine of theta and cosine of theta. Actually, sine of negative theta and cosine of negative theta. Okay, so let's just look at unit circle for a moment and imagine an angle theta and another angle negative theta. So that's theta, that's negative theta. Now up in the first quadrant, everything's positive, so let me just give that coordinates of x and y. And in the second quadrant, or the fourth quadrant, the x coordinate is going to be positive, but the y coordinate is going to be opposite of whatever this is. If I look at the sine of negative theta, sine of negative theta is going to be negative y. But another way to regard that is as the opposite of the sine of theta. So that is, that negative factors out. And because of this, this is an odd property of a sine function. Whereas the cosine, what's the cosine of negative theta? X, and the cosine of theta is also x. So it doesn't matter if you take the cosine of a negative number or a positive number, you get the same thing. So that negative for your sine function can factor out. And that negative for your cosine function disappears. So a couple important identities to know. We'll use those in section 3.4 and lots of other places. Once you have these, you can find identities for, say, the tangent. Tangent of negative theta is the sine of negative theta over the cosine of negative theta. By what I have above here, that's negative sine of theta over cosine of theta, which is just negative tangent of theta. So, okay. A little extra background as we head into problem 66 here. What's 66 look like? 2 sine squared of theta equals 3 times 1 minus cosine of negative theta, like that. So the first thing that I would do is clean this up. We've got a cosine of negative theta. What could I do in place of that? Yeah, just cosine of theta. Sure. Yeah, let's just write cosine of theta. So 2 sine squared of theta equals 3 times 1 minus cosine of theta. Doesn't matter if you have theta or negative theta. So let's just make it easier and write theta. Now, I'm stuck with sines and cosines in this problem, or a sine term and a cosine term, to be very grammatically correct. It'd be nice if I had just one function. And since my favorite identity is the Pythagorean theorem, sine squared of theta plus cosine squared of theta equals 1, I'm going to look to this to make a change. I'm going to try and get rid of the sines and replace them with cosines. So sine of theta, sine squared of theta is 1 minus cosine squared of theta. So I'll make that substitution. Now the reason I'm doing that is I'm trying to transform everything into the same trigonometric function. 1 minus cosine squared of theta. Okay. Let's distribute that 2. 2 minus 2 cosine squared of theta equals 3 minus 3 cosine of theta. Still looking like a big mess. But I've got a squared term, which kind of reminds me of the quadratic equations we dealt with in college algebra and in intermediate algebra. So I'm starting to think about getting a 0 on one side and factoring or something like that. Let me add 2 cosine squared of theta to both sides. And I'll subtract 2 from both sides. That gets a 0 on the left-hand side. And I get 1 minus 3 cosine of theta plus 2 cosine squared of theta. That's what I wanted. I wanted a quadratic equation on one side. Now, it may help you to kind of reorder this a little bit. 2 cosine squared of theta minus 3 cosine of theta plus 1. And even that, a lot of you might look at that and go, ugh, I hated these. And I'm with you. I was terrible when I was a student, and I took trig here just like you did. I was terrible at factoring these things. It might make it a little bit easier for you to look at. You want to do your U substitution? I think we did this one the other day. Let's just let U equal cosine of theta for the moment. So that's a 2u squared minus 3u plus 1. And at least that'll help us get past the factoring part. I know that the first terms have to be a 2u and a u. There's not much choice about that. The last terms have to multiply to what? 1. Not much choice in that either, right? 1 and 1. Since the middle term is negative, and both of these have to be the same sign, then both of these are negative. Yeah, I feel your pain. So the nice thing now is that either, since you have something times something equals 0, either 2u minus 1 equals 0 or u minus 1 equals 0. Add 2 or add 1 and divide by 2, you get u equals 1/2 or u equals 1. Meaning cosine of theta equals 1/2 or cosine of theta equals 1. And we've already solved that part. So yay. If you're looking at this and going, wow, that's a lot, don't worry. I don't put more than 8 or 9 of them on an exam. All right, just messing with you a little bit there. Terry? Yes. This is true. Yeah. You could have, what, divided out? Yeah. If you would have canceled it out, you probably might be losing a solution. All right, you remember at the end we ended up with cosine of theta equals 1/2 and cosine of theta equals 1. If we divide it out, I think we'd be losing a solution because we'd end up with a linear equation as opposed to a quadratic equation. So it's a good suggestion. It's very insightful. I'm impressed. But it, um, well, um, I'm not sure what law of algebra you would break, but let me show you like this. If I have x squared minus or x squared equals 5x, there's a couple ways I can solve this. I could say, oh well, let's divide both sides by x. Cancel out the common factor. That leaves me with x equal 5, right? But that's only one solution. Whereas if I have x squared equals 5x, and I move this to the other side, x squared minus 5x equals 0, and then factor out the x, now I get two solutions, x equals 0 and x equals 5. So I'm not really sure what law that you broke, but you can see that by dividing out that common factor, we've thrown out a solution. So yeah, that's a great question. I'm not really sure what to caution you against, but I think we would have thrown out a solution if we did it that way. Greg? Well, yeah, see, the thing that we're using here is you're kind of right on it, that you're using the fact that these things multiply together and give us a 0. And you're throwing away one of the factors here, so you're not going to find that solution anymore. So, yeah, it's a great question, Terry. I don't know what to say in general other than I wouldn't necessarily divide out a variable on both sides. Constants would be good, but variables, not so good. Sure. So the trick here was, I didn't like looking at this and thinking about factoring this. I'm like, that's just a big mess. So here's u, that's u squared, and that gave me this quadratic equation. And then to factor this quadratic equation, I know that the first two terms have to multiply to give me 2u squared. Well, there's not much choice there, 2u and u. The last terms have to multiply together to give me a 1. And again, there's not much choice. 1 and 1, or negative 1 and negative 1. And because of the sign of that middle term, we use the negatives. All right, good question. Anything else on this one? Okay, cool. Let's take a quick break.